Right, so I'm going to begin by recopying the equations a little bit bigger. Alright, so to solve a system with three variables in it, we need to pick two of the equations and eliminate one of the variables. It doesn't matter which two equations I pick, and it doesn't matter which variable I eliminate, whatever I felt was easiest. It looks like if I pick the first two equations, I can eliminate the y by first multiplying the top equation by 6 and then adding them. So I'm gonna multiply the top equation by 6. Doing so gives me 6x minus 6y plus 6z equals 66. And then we're just going to bring over the second equation. And notice that I can now add these two equations and the y's will be eliminated. So the reason why we pre-multiplied the top equation by 6 is to create additive inverse coefficients in front of the y's. So now we're going to add these two equations. Adding these two equations looks like it gives me 11x, and then the y's are eliminated. Looks like the z's are eliminated as well. And so I get 11x equals 66 minus 11 is 55. And after dividing by 11, I see that x is 5. All right, so we've got x. What's normally done is we take this answer and we plug it back in somewhere. Okay, so if I take x equals 5 and plug it back into maybe I'll choose the original equation, the original top equation. So let's see, maybe I'll recopy this. So here's the original top equation, and I'm going to plug 5 into this. If I put 5 in, I get 5 minus y plus z equals 11. And after subtracting 5 from both sides, I get negative y plus z equals 6. Now what we're going to do is take 5 and plug it into another equation to get another equation with y and z in it. It doesn't matter if I use the second or the third equation. I guess I'll use the second equation. So the second equation is 5x plus 6y minus 6z equals negative 11. Well, it's not necessary, but back over here on the negative y plus z equals 6, I'm going to divide the equation by a negative 1 just because I like to have that first term positive. That wasn't really needed. I just like to have the first term positive, so I went ahead and divided by negative 1. Alright, so now I'm going to take x equals 5 and plug it into this equation, the second one in the original system, so I get 25 plus 6y minus 6z equals negative 11. And I'm going to subtract 25 from both sides, so 6y minus 6z equals negative 11 minus the 25 would be negative 36. Notice that I could divide this equation by 6, and that would give me y minus z equals negative 6 after divided by 6. Alright, so what we would now do is take these two created equations, and we would have a system with two variables in it. We have y minus z equals negative 6, and y minus z equals negative 6. So before we keep going on, just to summarize what we've done, to solve a three-equation system, we begin by taking two of the original equations back over here, and we eliminate one of the variables. It doesn't matter which one. I ended up eliminating two variables, the y and z's. That I would say that normally doesn't happen. So what happened here is two variables got eliminated, and I got x equals 5. Now what I did is I took that x equals 5 and I plugged it back into any two of the original three equations I wanted to. And after we do that, we've created this over here in purple. We've created a 2-variable system. And we would eliminate one of the variables. Right, notice that if I add these two equations, I get 2y, and then, well, actually, you know, if I add them, neither one of the variables is eliminated, is it? You know, I could add them, but it wouldn't do any good, you know. But before I add these, how about we multiply one of them by a -1? If I were to multiply this bottom equation by a -1, it would turn into -y plus z equals 6. And then the top equation we just leave alone. And so now I'm ready to add them. A moment ago I was going to add them, but they weren't ready to be added. We didn't have additive inverses, but I multiplied the bottom one by -1. Now I can add them. And watch what happens. If I add them, the y's are eliminated, the z's are eliminated, and so I end up getting 0 equals 0. Once I add the 6's, you know, I get 0. This is called an identity. Whenever I get an identity like this, you know, like 0 equals 0, or 5 equals 5, 7 equals 0, you know, a true statement, whenever the variables all cancel out and I get a true statement, what that sort of means is that all numbers are solutions. What this means is y and z can be anything as long as they have this relationship, you know, like the equation is y minus z equals -6. You know, these two equations are actually the same. They're the same. It's the same line. They describe the same line. And so normally when we graph a line and we graph a different line, they intersect at one point, creating an ordered pair solution. But these two lines are the same exact line, so they're right on top of each other. And so that means all these points, you know, all these points on here, we have an infinite number of solution situation. That's what's going on geometrically. So again, normally this doesn't happen. Normally we get one line, and then we have another line, and we get one solution where they intersect. But these two equations are the same exact equation. So it's one line on top of another, and that's the reason why we're getting this infinite number of solution situation. And so when this happens, when we get a true statement, y and z can be anything as long as they satisfy this equation, as long as this relationship between them is obeyed. And normally what happens at this point is we solve for one of these variables, either the y or z. If we go back and look at the solution choices, if you look at answer choice B, it says the system has infinitely many solutions, and it wants me to describe in terms of variable z. All right, so the solution set is denoted as x, y, and z, and you know we just found out that x is 5, and it wants me to write the other answers in terms of z. So the second item in the solution set would be, in the solution triple, would be y. I'm going to solve this equation for y, and so we get adding the z, or moving the negative z to the other side, we get z minus 6, and so y equals z minus 6. So z minus 6 is what goes in for y. Notice what I'm doing is I'm expressing my answer in terms of z, like in terms of the variable z, like they requested up here. And then the third variable, z, we just leave it as z. And that's it. You know, this is the solution set right here. Anytime we have an infinitely many solutions, you know, this is often what the solution set will look like.